Good morning, guys. So it's a little blurred, but I think it's still visible, right?
I think it's a projected problem.
Whatever it is not a Java problem. So yes, I am Vaibhav and I work in Java platform lead. Okay, and this is my blog. I don't write anything. So sorry to go there. What we are going to talk today is the journey we have done for throughput to latency. Okay. Not audible? Not audible. Hello? Now?
Yeah.
Okay. So, anyone here from the hardware industry? Intel, AMD? No? Okay, because this is software talk. Any students here? So, thanks for coming. I think we need more students actually. Old guys actually don't do anything. So can you define throughput for me? Anyone? What do you mean by throughput? See, what is the truth is that I don't like questions, so I keep asking. Okay. So that no one will ask me questions. So what is throughput?
Amount of work done in given time.
So it's like a speed, is it? Okay. And what is latency?
Time taken.
So is that latency is directly equal to time? Good man. I like that.
The barrier is.
Yes.
Yes, actually it's true. So latency is a direct unit of time. Means I need 10 hours to finish a work, 10 hours is my latency. And how fast I do the work, that is throughput, as someone have already explained. So it is time done per unit second. Okay. So if I am manufacturing a car and I am making 120 cars per day and I am working for 8 hours, then 8 hours is my latency and my throughput is 120 cars per day. Okay.
Why it is not per 8 hours?
Why it is?
Why it is not per 8 hours?
It's perfectly fine. You can convert into per hour, per minute, per second. If you go to the software, per nanosecond also.
No, as you mentioned, 13 cars per day.
Yes.
My latency is 8 hours.
Yes, because I work only for 8 hours.
So yeah, so I can
Okay,
say
but the rest of the 24 minus 8, I am not doing any work. Okay, so you have to consider per day work. Okay.
that day working to
Yes. Okay. So what we are going to discuss, I will show you some of the hardware equipment. This is one of my most favorite slides. And then I will show you how we have done the code journey. You know codes, right? Anyone who don't know the code? College guys? Code? Okay. Then I will talk little bit of the latency and throughput. And actually latency and throughput is very much related to concurrency and parallelism. Okay. So as you told, latency is how much fast you can do, and that is what parallelism is. Okay, parallelism has nothing to do with anything else. You just have to finish your work fast. That's it. Okay, and I will talk to you how to achieve the parallelism. And some examples I'll cover in between here and there. Yeah? Have anyone of you have seen this slide? Okay, this is one of the most, not very old, it is small. Okay. And whenever this slide comes, we talk about Moore's law. Okay. So I don't know what is Moore's law. It said something doubles every year. So the green line here is the transistor. Okay. And this is the intensity I am talking about. So you are seeing that how we are increasing the number of transistors from 1973, I think that time when Intel get started, to 2010, right? And it is perfectly following the Moore's law. Almost little more than Moore's law. It is going almost exponential. Yeah? And the blue line here is, it is visible, it is called clock speed. So you know what is clock speed? Clock speed directly tells you how much time it takes to execute something, right? And we were doing very good and we were very happy, but suddenly in 2003, we got a flat curve for the clock speed. Because you cannot do things faster than the speed of light. Okay. So it got a blockage. And this is your power dissipation. So we saw that our hardwares are getting limited. It can actually consume or it can release a limited number of power. Means it cannot take overburning. Okay. The hardware cannot overburn himself. or itself. Okay. And this is some of the dirty tricks we play with the processors. So let's not talk about this. So you can see now the instructions we are executing per second, we cannot increase it. Are you agree with this? Because this is instructions execution, we cannot increase it. And we have a flat line from 2003. Okay. It will go flat. Till you will not beat probably Einstein and tell that something we can do more speed of light, more faster than that. But we are doing very good in terms of number of transistors. Are you agree? Okay. Then it's a very simple job for Intels, right? They can just make more cores and they can just put more transistors, right? And you can just use those cores and you can run things faster. But the dual core machine almost came around 2000 time frame. Okay. And if we are in 2016, I think it came much before than 2000. If we are 2016 and if we are following the Moore's law, we should be on 32 core, right? But how many of you use 32 cores machine? Anyone here? I use. Okay.
24 to 12.
32 core for what?
Telecom operator.
Right. But no laptops, right? No laptops, right? So you maximum reach to 8 cores, right? Or maybe 16 cores. Some guy will have super fast laptop there, maybe 16 cores, right? So what happened? What went wrong here? Can you tell me? I mean transistors I can increase number of cores and I can just leverage that cores and I can use.
Even the number of transistors is not it's facing a problem in 2015 and 16. 16 and 17.
Ah yes. So my data is right. Yes, even the transistor, because I will tell you the reason. Okay. Yes, please.
Power
No, till you are just keep adding the cores, the power dissipation will not be a big problem. Yes, please. Parallel, okay. We are talking about parallel. Why?
There are
Yes, so I will tell the same thing which you told in a very bad word, that we are not capable enough to use multiple cores.
absolutely.
Okay.
Absolutely.
So as a software engineers, we are just useless. We cannot use that much code. And then, sorry, that is how I talk. So actually, even the Intel can provide you more cores, but as a software designer, you cannot leverage the cores, and that's why Intel stopped producing more cores. Okay, it can anytime produce more cores. Yeah. Yeah.
This is language problem. We don't have language.
It's a language problem, it's a software problem, it's a problem of everything. Where is the morning guy who was talking? Where is the sir? Yes. So he told a lot of good paradigms. So good paradigms come from presentation and it goes to your notebook and finish. After that, no one uses it. So the journey of good paradigms goes from this to this. Okay. So that's why it's a challenge for the language to put all these things at the language level. So that even if the software is written very badly, language should handle it. Okay. That's true, right? I mean, anyone disagree with the fact that you don't write bad software? Right. Because things will happen that manager will tell you, oh, let's come for a meeting, and you will tell, no, I'll finish the job. Don't call for meeting. And then that night you are going to write the software. That is how it works. It's anyway. So this is a hardware trend, remember this. So according to the time, even the performance definition has changed. Okay. First, we used to have a very good life with a single core time frame, right? Even people became greedy in that, and they want things to run so-called parallelly. They want to show that things are running in parallel. So we came with the logic of non-blocking and prioritizing, right? So non-blocking is nothing, it's just an out-blocking when you try to fool a user that things are running in parallel, right? Then you reach to multi-core time frame. And there you started focusing on better throughput, right? You try to leverage your CPU cycles. You want to put the best CPU for you, the best core. Oh, what is your measurement? 2.6 gigahertz, awesome. Okay, so that happened. But then you came into the many core time frame, okay? And then you started focusing on latency, okay? You want your things to finish fast. It is as simple. Okay, latency has nothing to do with the processor level work. Okay, it is your software application which can finish it faster. Okay, and bad luck guys like me who runs the software, who makes the software like JDK, we have to deal with all these three people. Okay, and we have to write a generic code which should run everywhere good, else people will be sad. Yeah? Any doubts? You can ask me. Okay, this slide should not be here, but anyway, I will just show you a JDK release trend. The same applies with other languages also. So very early we will have threads, locks, and condition queue, which is just good to do prioritization or round robin. Then we came in between. We came with the concurrency and the blocking queues, which can be good to provide a concurrency level one. Okay, and then now we came on to parallel stream. So which is just to parallelize the things. Okay, so this is the same trend if you can see other softwares. Okay, either you can take .NET or anything else. So as the hardware is changing from here to here to here, right? We are changing the software. So we are changing software according to the hardware. Okay. So now, okay, I will not show the same. Can anyone tell me what is the difference between concurrency and parallelism? I mean, it's a very old debate. Yes.
Concurrency gives us a false impression that it is happening in parallel.
Okay.
There is that context happening.
Okay. So if I give you multi-core machines, is there any concurrent thing that will be there? It can be. Okay. And something can be parallelized also there?
Yeah, in case of multi-core.
Okay. So
To
yes.
achieve concurrency, you need to parallelize things, right?
Yes. So the fact is that concurrency is tough, and concurrency is about structure. Okay. And parallelism is about execution. It's as simple as that. Okay. When you make a proper structure for your code, that is concurrency. When you run your code faster, that is parallelism. Okay. Parallelism is damn easy. It is just take your task, divide into two, and just run it in parallel, and then combine the task. As simple as that. But concurrency deals with all the mutex, semaphores, race conditions, lot of things we need to do. Okay. So in a single word, I can say concurrency is tough and parallelism is easy. Or for more knowledgeable person, I can say concurrency is about structure and parallelism is about execution. Okay. Any doubts?
Can I ask about a real world example?
Of what?
Parallelism is like driving the car and speaking to someone else in the phone. Parallel.
Okay, you reminded me human mind. Human mind is serial execution. Human mind never do two things in parallel.
Subconscious mind is driving the car and your conscious
Yes.
is talking.
Now you came into another concept.
Sitting and watching TV.
Yes. So either you are eating or you are watching the TV. When you will concentrate on TV, you will not eat, and when you are eating, you will not watch.
It's just that the context switching is.
Yes, but it has a better concurrency.
It's a concurrency.
Yes, human mind is very concurrent. Okay, it can do a context switching very fast.
Anybody read Men Are from Mars, Women from Venus, or that something?
Yes.
I think men are serial and women are parallel. I think that's what I think.
Yeah, when women go parallel, actually, men will not be serial also. They'll just go and we have lot of moments in this. Yeah. Okay, now I cannot see the time. Some Unix is script is done. Anyway, we'll come back. I'll show you the example for each and everything. Yeah. So parallelism is about optimization, faster result, that's it. Okay. Don't think parallelism for anything else. You analyze the problem, you implement the problem, and then you test the problem, and there you will get to know about the parallelism. And after the test, you repeat the process. Okay. So because your statistics can only tell you that you are parallelizing the workload. Okay. Your code or your nothing can tell you. Okay. If your results are not good, in none of the cases, just go for the sequential. It is as simple. So why you think that parallelism can take more time than the sequential one? Is that any case where the parallel can take more time than the sequential one?
Yes.
Yes. Why?
Synchronization among parallel works.
The bad division of a problem.
Also
into
dependency between these two, it has to wait for that to finish.
Right. You all put the point. So this is what happens. You have to decompose your task, you have to manage your task, you need a manager for this, and you have to combine the result. And with this, you have to do this job also, which is the most important job, you have to solve your problem. And if you are doing a sequential run, what you have to do? You just have to solve it. So there is a big time that goes here. Okay. Your data structure is good for the decomposition? You don't know. Okay. So let's see. So parallelism will always give you a slower start. Okay, because it has to do this much of job, then only it can start doing it. Right?
It can be faster also.
It need to be faster, else we are all fired.
You are saying it is slower than sequential.
It can be slower than this serial. Okay. But by knowing the right method, we will obviously have to make it faster. Else there is no use, right?
For example,
Python, what is Python? It's a snake. No, I don't know. I don't know.
Java better. Java better.
Sorry, what was the question?
No questions. Okay, so parallelism deal with this is the four what the sir was telling in the morning sutras, right? This is the four sutras, right? I have not written, but from next time I will also copy your stuff. So a problem that can be broken in the parallel. This is most important thing. Can you tell a data structure which can be broken in parallel?
Your enum and
Array.
Array, yes, who told array? Yes, thanks sir, you are still stick to the basics. Okay, and can you tell a data structure which cannot be broken into parallel?
Linked list.
Linked list. Linked list you cannot tell go into middle. That's it, as simple as that. Array you can tell okay middle and then again middle. But linked list you cannot tell go into the middle. You have to go from the start and reach to the middle. Right? A very good implementation that is required, that is the responsibility of new software engineer. A good runtime support that we will take care of it. Okay. And then a minimum data to get benefit. Okay, this is one of the most important things. You cannot tell that I want to sort a 10 element, I want to do it in parallel. Okay, it is just nonsense. You cannot even think of doing for 100 or 1000 elements. You need to go beyond element, then only you can think of parallelism. Right? Because you know there is not a parallel cost that goes. Right? Yeah? Any questions on this? Actually, every slide will be very simple like this and it will finish. So, okay, here I am showing you an example and I will explain you data flow dependency. I don't know how many of you make that while you are running your software. Again, this is one of those paradigms which we should use but no one uses. So, G of n is actually depending upon f of g of n minus 1. Okay. And if you will make the data dependency diagram, actually G3 is depending on G2, G2 is on G1 and G1 is G0. And then you will get F0, right? So it's a straightforward dependent diagram, right? There is no doubt about it. So you cannot do parallelism. It is as simple, right? It is just waste to even think of parallelism. Okay. But I have just changed my function a little bit. Okay, it is very similar function. I have made g of n equal to f of n plus g of n minus 1. Okay, and then you will get a graph like this. If you will see this graph, you will feel it can be partially parallelized. But you can change this graph into this. Okay, because it is actually this plus this plus this, right? So here you can exploit parallelism, right? So that is the term we use, that is called exploitable parallelism, where you have to actually find out the parallel things can be done on. It's a simple diagram. I'll just come to the example. Wow.
The F0 is that G2 is depending on F0. F0 is not depending on the other diagram. It's not dependent on.
Yes, because we have changed the function, right? So this is different function and this is a different function. Okay. So this function cannot be parallelized and this function can be can exploit the parallelism, right? I'll just take a simple example, most easiest thing. Okay, summing a array. Okay. Do you think this work can be done in parallel?
Yes.
All agree?
Yes.
So there is anything wrong in this implementation? This is such a nice implementation. I just made sum equal to 0, and whenever I show this to someone, we tell this can go for an overflow. Okay, please don't go for the overflows. Then in the for loop, I'm just adding the sums, right? And this should work, right? But what is wrong in this?
But seriously, you keep adding one by one.
Oh, this is a sequential.
Sequential.
Okay, and we are greedy enough. We are not happy with this. Okay.
You made.
So yes, this is actually bad, and you should unlearn something called accumulator pattern. So you are talking in the morning which pattern we should learn, and we talk actually which pattern we should unlearn, and that's our job. Okay. So this is called accumulator pattern. Okay. Never accumulate a value in a data structure. Okay. So here this is bad, and then this for loop is bad. Huh? Because it is a serial for. It's not bad, okay. I know that you're buying it. It's not bad. It's not good, okay. So what we did is that, okay. So what we can do, actually my animations are lost, so I cannot show you. What I did is that I have broken this for loop and I have written in concurrent. Okay. I will break this for loop into two parts, and I will run both the parts concurrently. Okay. Do you think this code is good enough? So here concurrent means I will just give this part to one thread and this part to one thread. That's as simple as that. Okay. I don't want to use any Java or anything. Do you think this is good?
No, not good enough.
Not
good enough.
Not good. No. It is not good enough. It is far. It is wrong actually. You have to come more basic. Okay. Because just forget about this part. Okay. You are using the sum as the same variable, and you are giving it to two different threads. Okay. Two different threads can change the value of sum. So you will not end up getting a right value on it. Okay.
Oh, the sum is a global
Yes,
variable.
you will not end up getting a right value on it. So what you have to do, actually you have to make this operation atomic, and you have to make this operation atomic. And now it is good?
By atomic you mean the sum is different? What do you mean by atomic?
Atomic means synchronized. If someone from Java, I don't know how we handle in .NET. Is it synchronized keyword?
Yeah, but finally the return sum should be, you should add up both those sums and make it.
That's your next question. So yes, you got the point. So this actually logic will sucks. Okay, because you are synchronizing on a variable called sum, and this will always go for it again, right? This code will block this code, this code will block this code, this code will keep blocking this code, right? And this is not at all a good logic, right? So why is it not a good logic? Because we are not using a good pattern. Okay. What we are doing, we are spending too much time in safeguarding the data, right? And the best practices that we keep shouting and no one listens that is that first don't save, then don't mutate, and then come for the coordinate access. Don't save is very simple. Don't save a variable. Don't mutate means don't change the variable, and coordinate access is what the bullshit we are doing here, right? Putting a synchronized table. This is called coordinate. Okay. And you should always start with this and then go this and then go this. Okay. So as you told, it's a very simple thing. Why we have to write this logic? We can just change a variable called sum1 and sum2, right? Or we can take left and right and we can just return sum1 plus sum2 or left plus right, right? Now can you see that anything is messed up with the synchronization here?
Means both should be finished before you can do the return.
Both are getting to different threads. Yes, that we have to wait for the thread. That will always be there because still the right value will that will always be there. Yeah. So this is fine, right? This solution looks good, but someone has still had the question. What was that question? It's not good enough.
It's not good enough because you assume there are only two things.
Okay, so I will not assume that in the next slide.
So
Okay.
you can see the other extreme. If you are a poor guy, you are running on a single core machine, this will suck. And if you have a big machine with 32 cores, you are using fully utilizing.
This will should we say suck? No, it will be little bad. Okay. Please don't go for the wrong nomenclature. Suck means very bad. Okay, it will go little bad. Yes, it will go little bad. 100%. Okay. So this is a generic code for parallelization. This is the golden code. Okay. If your problem is smaller than sequential, just finish it off. If your problem is more than sequential threshold, just break the problem into left, right. Keep breaking the problem till it will not be smaller than the sequential. Any doubt in this? Shall I say it again? If your problem is smaller than sequential, just finish it off. If your problem is more than sequential, keep breaking it in the left and right till it is not coming into the sequential. Okay. And then you should return combine of all the results, like the success, right?
So how we can identify that the problem is latency?
How you identify? You have to sit with a pen and a paper and you have to do statistics. Then you can only identify.
How can I assume how big my data is? It's program, right?
It's it's in the next slide. It's here. That's all. Okay. So that's one of the biggest challenges actually. So okay, in Java we say fourth-hand framework. I just think that it's a normal parallelism paradigm. You divide a task into subtasks, keep dividing that subtask till it will not become a very small subtask, and then keep joining, and then you will get your work. Okay? This is a normal thing we do. And just to make you happy, I can show you some of the values. So what I did, I was doing a sum of 50,000, 500 k elements, right? So it is 5 crore, more than that, right? Whatever. So if I am not dividing the problem into smaller, I am just using the complete thing. In 2 thread, I am taking almost the same time. In 4 thread, the time is going down. In somehow 8 thread also, I am taking the same time. Maybe something wrong with my analysis. And in 32 thread also, the time is going down, right? And now what I am doing, I am breaking the problem into 5k. Okay. So 5k is actually my sequential implementation. When I will tell, now run it sequential. Don't go for the parallel. Okay. So you will get a great time. Okay. In 2 threads, it is 1.02. And in the 4th thread, you are almost reaching to 4. In 8th thread, you are reaching to 6. And 31st thread, you are reaching to 70. Right? And as you mentioned the question, someone can tell you, maybe, why not this? Okay. This is also giving me 7 times faster result. Right? It is just about getting the result faster, right? But when you actually do this analysis, you will understand how you have to break your task. Okay. And here what we understood is that 5k is the right element when I have to break my task. Okay. And in the real world, actually the data is unknown. How much data is there, we don't know. But we need to put our analytics to get how much data is there.
Yeah, and it hard codes to the hardware, right? So this is true for this CPU with 4 threads. So supposing there's another CPU with 4 threads, this number will change. Am
Yes,
I right?
100%.
Yes, is second one is a faster.
Which one?
Numbers.
This is faster. This means it is running 17 times faster than the serial. One core, serial. Okay. And core and threads are two different things. Don't get confused, because in Java, per core we make 2 threads. Okay. Because there is some hyper-threading concept and some lot of nonsense concept at the core level. Okay. So Intel claims that on one core you can easily make 2 threads and you can parallelize it. That's why at the Java level we always think that one core means 2 threads.
Does it work?
It works. That means they're right, right?
So just check.
So is it just a concept?
It's just some data which I am showing you. Okay, this data can be wrong anywhere else. Okay. So yes. So now we have to do the performance consideration. The same question which you have asked. So first of all, your performance consideration is how good your blockchain can be blocked, right? So if you will go for a array, it is very good. What about the array list? Anyone can tell? Any Java have an array list, right? You don't know array list?
How will you break it? I mean, the breaking itself is a challenge. First of all, we need to go to the middle and break, and somehow you have to break.
In array list you can do it, right? It's just an array.
Yeah.
Right? So you can do it, right? Okay, but still the performance will not be good. But linked list, you know, you actually you can never parallelize it in this. It is as simple. If you go for some kind of tree kind of dependency, it is good. It is okay kind of thing. You have to see the task management cost, right? You know the task management cost. You create a pool, you create a queue, you keep putting your task and a lot of things to do. And then you should see a combination result. That is also very important, right? When you are adding 2 numbers, it's a very simple combination. But what if I tell you that you have to combine 2 hash maps? It will just suck out. I mean, it's a very complicated operation. You cannot just combine 2 hash maps. So I cannot make my subtask, and in the end I will keep combining all the hash maps. It is not doable. And then I talk about the locality issue. Anyone know about the locality issue? In Bangalore, actually, locality issue is very much. Yes, please.
So it's the cache, right? So there is a locality and reference.
Yes, it's actually cache miss. I will explain you how the cache miss. And anything goes wrong in this, your parallelism will go wrong. Okay, it's as simple. Anything will go wrong. Okay, even one thing will go wrong, it will go wrong. Okay. Any questions? It will come. Everything will. Okay, and let's
Just to
start.
check my understanding, so
Yeah.
till now I was thinking, okay, parallelizing a problem, dividing a problem into parallel. The number of parallel is directly proportional to the number of pores or into 2.
Yes.
That's not the case is what you are articulating.
Yes, it's not the case. Because with that you have to consider a lot of other things. And that is what we are considering. Okay. Like one thing I will tell you about the locality. And I am 100% of sure no one are part of your NQ model, right? Anyone? NQ model is a simple model which will tell you that how much element it need to be. Then only you should think of parallelism. Okay. So your n into q should be greater than 10,000, where n is the number of element and q is the operation you are doing. So in sum it is 1. But if you are doing a square root, actually it's not 1. Because square root at the atomic level is 4 operation. Okay. When you do a square root, it is 4 operation at the atomic level. Okay. So if your element is say 10,000 and you are doing a sum operation, good enough. You can think of parallelism. Actually still you should not think. If more than that you should think of. Okay. So this says minimum data. What is the minimum data when you should start thinking of parallelism? Right? Source splitting, I have already told you some of the source is awesome, some source sucks. Array logs, array list is still not so good, linked list sucks, big good, okay. Right? Here comes your locality.
So
Yes.
it's a linked list, right?
Yeah.
So you are saying that to make it parallel converting array list, then you do.
Why the heck you are putting into the linked list?
In suppose I want to do parallel list.
Yes. Yes. I mean, putting a linked list into array list is like, it will take all of your day. Okay, it's a very damn complicated operation. Okay. The linked list means everything should be tested. That's the beauty of linked list. Right? Okay, locality is, as we told, locality is dangerous. Locality is directly means cache miss. And I will show you what happens when you write integer and what happens when you write int. Okay, so I cannot draw anything. Okay, leave it. I will just draw fictitious. So what happens in the array is that your memory is like this, and everything is a contiguous memory location. Okay, this is what happens in the array. But when you will say Java integer, okay, you should understand that integer array, everything inside is a class, right? So inside it's this memory location where every address is pointing to a class, right? It is pointing to a different class, right? And those all are living at different place in the memory, right? So if it's an integer array, it's a normal array, okay, your processor will be the most happiest person. Okay, it just know that I have finished this job, next job is just the next address. And after that it is keep going, just keep going, right? But when you go for the integer, your processor will not be happy because it don't know where to find out. Okay, it has to go to that memory location to find out. So that means it cannot be cached, right? It just cannot be cached. Here I know I can cache it because I got this. I know the next thing I will get is this. Next thing I will get is this, right? But here it is pointing something else. Here it is pointing something else and something else. And that's why when you will run on integers or something like the classes, it is going to take a lot of time. Okay, so never think this is a good split. Okay, integer will not going to give you a very good split. And this is the data. Okay. Yes.
What about memory? We will consider memory in that context. So, in case of int, it will be
Contiguous memory.
yeah.
Right. In case of integer, it is not a contiguous memory. As simple as that. Yes.
So at least some kind of benefit we are getting, right?
In which?
In integer, because you get a story distributed wherever this is.
No benefit. Just that okay, even if your memory is not contiguous, it can store the data. It is as simple as that. That's the benefit.
And there is no continuous space in RAM, so
Int will not fit. Possible. Int cannot fit it.
yeah.
Okay, that's possible.
What about an array of structures and I want to, the third element I want to total. So depends on the size of the structures. All, will it cause a cache miss?
Yes, so cache line miss can be possible in that case also. Okay, cache is the one of the most dangerous industry, and I don't know who is the finder of this cache. So these days it's a typical problem that in a distributed system, you will have one processor, you will have two processors, you will have some shared data, right? So this shared data, they will have a cache, this processor will have a cache, this processor will have a cache, the operating system which runs have a cache, and the language which runs have a cache, and then people will make cache in their software also. Okay, so I mean you don't know how many caches are there, right? And the caches simply means that I try to read something faster, okay, and it never works. Actually, it works sometimes. Okay, so this cache complete business is very risky now. Okay, and since your CPU speed is not increasing, you are just keep making new caches. If you see Intel is increasing cache day by day, right?
And to answer GQ's question, we have two approaches, right? Array of structures and structure of arrays. So if you take structure containing array of elements, then your cache, you are friendly with the cache.
Yes, that's true.
Vaibhav, we have this array.
Wow, so many people have given a good answer, man. There are a lot of things.
Let's keep on going.
Guys, now I'll show you. Okay. So now you should not asking questions, replying that. So yeah. So this is one data you can see. On 1 billion data, my normal integer array on 8 core machine is almost 8 times faster. It is so good. But you can see integer is almost not even 4 times faster, right? And if you are just considering 1K data, it just works. Yeah?
But modern languages, for example, if you take Python, everything is an object here. So in that case,
they do lot of low level optimization actually. Even in Java also we do a lot of low level optimization, but most of the languages do that. Okay, so they will just take an integer from you, but you don't know what they internally do. They can convert into any primitive data.
so that way array of so looks like it's a primitive, but it's not a primitive.
It's not a primitive. I don't know how the Python handle it, but in Java, if you are writing integer, it's not a primitive. And in Java 10, actually, we are making integer also a primitive. There will be something we don't know what to do. Okay, so this is good. So I think I am almost going to be over. Yeah. So let's repeat. Okay, what you have to consider for the parallelism? NQ understood? NQ? NQ should be model? Okay, I cannot give it. Low cache miss. Yes, he has explained the low cache miss. So you have one cookie here. Good source of splitting. Combination cost should not be high. And the most important thing is that pipeline order should be insensitive. You understand that?
No.
If it is a sensitive order, like we have shown you, right? The next data is dependent on the previous data. You cannot just do parallel, right? So the whatever you are putting into the pipeline, it should be insensitive operation, just like sum. Okay, sum and all is very actually it's risky sometimes. I'll tell you one example that generally we often give. So your int a equal to 1, right? And your int b equal to 2. And you are saying a plus b, right? Now here a plus b is a transitive operation, right? So the order doesn't matter, right? So what I can do, I can make b equal to 2 up and a equal to 1 down, right? There will be no problem, right? And now I am writing a logic here. If b equal to 2, print 1, print a. Okay. Now in that case, you cannot change the order. If it's a multi-threading operation, you got the question?
Yes.
You got the question, right? Or I have no, it's a PDF. So a equal to 1, b equal to 2, a plus b. Now these two operations are insensitive of order, right? You can change it. But now I am downside writing somewhere if b double equal to 2, print 1, print a. Okay, you are 1, right? You cannot make that order insensitive order, right? And this is what most of the compiler do. They think that these two are insensitive, I can change the order. In this case, they will not change it because they are not getting some advantage. But in many cases, they get advantage. So this changing the order is a very risky job. And that's why we put a term called as serial as. Okay. So whenever you do parallelism, whenever you are changing the order, you should follow as serial as. Means changing order should behave as serial as it was before. Okay. And Java comes with a keyword called volatile. I don't know what kind of keywords available in other languages. But these are all fake fixes. Okay. Things like volatile.
I'm holding a question. So NQ is 10,000, right?
Yes.
Where is 10,000 came? It's Intel.
It's a claim by Intel processor. The NQ model is an Intel processor model. Okay, we just follow it. Actually, as a Java developer, we have the very good time when Intel guys come and tell that what you are going to put next in your language, so that we'll make a good processor for that, and we feel very happy. Okay, because a level downside is asking you that what you are going to change. So don't know what about the future, but currently it's good.
All the programs become like kind of hardware dependent, or hardware optimized, right? Kind of breaks the like write once, run, running.
Yes, Java is still not hardware dependent, but if we will be hardware dependent, we can run things much faster on that particular hardware. And then you will reach back to the 60 years old thing where you just write a software for one operating system and you keep porting in all. So you will have a team which just do migration, okay? And no one do like migration, okay? So you just make a good software on Intel, and then now you have to put it on AMD, and you have to port it from IBM operating system to Windows operating system to Mac operating system to Solaris to Linux everywhere, right? Because you are writing a hardware specific instructions. Right?
But then to get parallelism, you need that, right? I mean, that 10,000, if I move my code from an Intel to an AMD processor,
the figures can be found out. Okay, these processors almost behave very good in almost. I mean, AMD is just Intel company, right?
no, I mean, like,
They just make the same processor.
no, I mean, like, if they have more GPUs, make it different.
Yes, lot of things are actually dependent on hardware, and to actually leverage the hardware speed, you have to be hardware dependent, which Java is currently not, and that's why Java is a slow program. Okay, I don't have anything bad to say that, but Java is a slow program. Compared to Java. It's not. We started doing a lot of optimization, and the best thing I am seeing in the new programming language is that they are making the data structure like that it need to be always faster. Okay, but we have a backward compatibility, so we cannot break our data structure apart, right? Because Java gives the backward compatibility. But now all the new languages which comes with such a good data structure that you cannot just do anything. They will tell you at the compile time only you have to tell it's null or not null. That's it, as simple as that. Okay, but in Java I don't have that much freeness. Okay, and you know if you are telling null or not a null at a compile time, it can solve a lot of problems. Because having a null in the address is just a memory fault. Right? Okay, freelance is over. This is article. Okay, but freelance is going to start, right? Okay, so freelance is over is an article which says that you cannot leverage more of the processor speed now, so start doing some work. Okay, because you cannot keep increasing your processor. We have 8-core processor and we put 8 core into mobiles also now. We are done. Now you have to write a better software to get faster result. And iPhone still works very good with 2 core. Okay, but you will get all the companies with 8-core processor and you will just it don't run. Okay, because it's a software dependency. If you write a good software, if you make a culture of writing good software, it will work. Right? And this is some talk on the parallelism. It's our talk. That's it. Any other questions? I'm sure there will be no questions.
So should
Any benchmarking tools you would recommend out of this?
There are a lot of benchmarking tools. We use something called Java benchmarking, Java micro benchmarking, JMH. But there are a lot of good tools and a lot of intelligent tools that are available in the market. I can just give you the link. But most of the benchmarking tools, you should just use it on the command line. Okay, you should not use it with ID, because ID do their own kind of optimizing. Yeah. Yes, sir. Your question.
yeah? So hearing all this,
Your software.
what sutra should I add to my sutras so that it becomes good for parallelism?
Freelance is over.
Okay.
Freelance is over. That's it.
I think
Start doing some work.
one standard thing is like mutable state is bad. Basically. That's what I.
Yes, mutable state actually it's a very good thing, and we discussed last time also. So it works good if you are making a software for servers, but it is not good if you are making for a very small kind of devices like for the Android. Android good practices are to make an object immutable. That is one of the best practices of Android. Make the object immutable. And when you will come on the Java, we'll say make an object immutable. That is the best practice, right? Because
So why is this difference? Why is there a
if
difference?
immutability means if you have changed something in the class, you return the class,
Right.
and you give the newest state of the class, right?
Yeah.
And mutability means you keep changing something into the class.
Right.
When you are giving a new class, you need a lot of memory,
Right.
So if you are on an Android machine where memory is a limit, you cannot keep returning your class. If I am going into the recursive loop and if I will keep returning a class, it's a huge memory. Though even the memory will be cleaned very early, but you cannot. Your RAM will just burn out. And we have seen a picture of RAM burning also, right? We cannot burn RAM further. It's almost burning.
So you're saying that whether mutable or immutable depends on the memory.
Yes.
Okay, to add, don't create a garbage collect objects at the CPU speed. So let's say you.
That's perfectly right side. Don't collect the garbage, don't make the objects at the garbage collector and the CPU should keep doing same job. Okay, you are making the object and garbage collector is cleaning the object. Okay, that is what happens in mutability at many times. Okay, like I said you are putting a recursion and you are returning a class. Your next class will be of no use, right? Almost the top class in the stack is only used. Rest of the classes are not used. So garbage collector will keep cleaning. Okay, so noise.
CPU is.
Yes, CPU will burn.
Battery will drain. Now the reason for battery draining.
Any other questions?
Yeah, you're referring to one language. Are you referring to Go?
Yes, I have referred to Go many times. Go is one of the very good language which talks very good about the parallelism. Yes, that's true. Go is by Google, is it? Go is by
Good,
Google.
yeah.
Google guys make something good.
C++ compilation was slow, that's why we started.
Yes. Okay, time is over. Thank you. Thank you.
Just find your both are open.